Cancel. I'm recording all this. I'm recording your bickering about rides home after doing dishes. All right, we are going to continue on with the note. We've got actually 2 days worth of notes. We've been doing lots of labs. So now we're going to talk some chemistry. And actually, again, I haven't taught this for quite some time. And I think the last time I taught this, I wouldn't have done so many little labs at the beginning. But you know what? Thinking back, I'm realizing, hey, no, this worked out really well. We got to use Google Classroom quite a bit. We got used to making documents. We got used to filling in some stuff. So that works really well. So what have we done up to this point? Well, we've talked about how we describe matter with physical and chemical properties. We talked about physical and chemical change. We used the physical properties in order to identify some unknown substances, and therefore that's a very important skill to be able to do tests, observe, make good observations with our 3 adjectives, and then be able to come up with some conclusions like the identity of the substance that we did. Excellent. The last lab we did, we looked at the physical versus chemical change, and that was excellent as well. Again, practicing observing those properties. It's a very important skill. So now we're going to change gears a little bit. We're going to kind of step away from the experimental part of it, and we're going to look at some chemistry in terms of the theoretical part of it, the way we think about chemicals, and the way we and the ideas that we have to express those chemicals. So we're going to talk about matter and how we can classify matter and break it down. And so, yes, we are going to write that particular chart. So you at this point can write that chart down. And then we are going to define the terms that are found on this chart. And this is the starting point for pretty well any chemistry class, even in university. I remember our first year university, we started out with this breakdown because this is the fundamental way in which we look at material as chemists. You looking for the note? Here, you go, you write. Okay. I'll find it for you. I don't know why this is, but when it says unable to access with the account, I switched it to your non-school Google account, and then it opens up. And I have no idea why that is. And I've found that with other things as well. Okay, so what does this represent? This kind of represents the way human beings have dealt with matter as they've encountered it, all right? So if you have something, a container of material, or perhaps a gas that you've trapped, or perhaps a rock, or perhaps something like a mineral, something that is more simple than a rock, not necessarily have all those little pieces in it, but looks nice and smooth and shiny and that type of stuff. If you have a piece of material, you can then go through this chart, and you should be able to find a spot for it to classify that material. All right? So let's say you had a bag of bird seed, which is made up of all those different types of little seeds. You could ask the question, all right, that bird seed is made up of matter, but where do we place it in this particular chart? Now, bird seed that's made up of all these different types of little seeds would end up in a mixtures category. It's a mixture of different seeds. In actual fact, it would end up as being a heterogeneous mixture because it's got these different parts all kind of mixed together, all right? But you could also take a hunk of gold, and you could go through the same process. What is this thing? Is it made up of two or more things mixed together? No. Is it a pure substance? Yes. And we could trickle down, and we could analyze all of these things, all right? So we want to be able to analyze these things, or analyze material using this particular chart. So at this point, I'm going to continue on, and we're going to define some of these things. So we'll bring it up and define mixture. You see, he said that you use your phone. Normally I see it up here, but you're trying to use it for evil by sending messages. So what you did was you took it off of your desk and then you hid it underneath. So as soon as you do that, I know you're sending messages. See? See how that works? Yeah, keep it up front. Use it for good. So again, I talked about an example of some bird seed. This is a mixture. Why? It's made up of two or more substances. It has a variable composition. That means you can get it in varying amounts. Sometimes you can get bird seed that's made up of mostly sunflower seeds, and then maybe some of those other little seeds. Or you could get it the other way around. It's mostly got the other little seeds and got a few sunflower seeds. You know what I'm talking about, the bird seed? The little round guys, some of the little birds like that, the finches like it. Then there's the big bird seed. You know what I'm talking about? Or the sunflower seed? No, you don't feed the birds? All right. Anyway. Variable composition. May be separated into pure substances by various separation techniques. Separation techniques can be as simple as separating it out with your hands. Be a lot of work. If you have a sieve and you've got the larger pieces and the smaller pieces, you could use a sieve. These are what we call physical separation techniques. We're separating them physically. You could use a magnet if you had metallic pieces. I grew up on a farm. I remember we had this mill that would grind up the dried corn and mix some vitamins with it with some soybean meal. And in the back of this device, every once in a while, you had to pull out this row of magnets because the magnets are designed that if any metal pieces get into the feed as it goes past the magnets, it grab them up. It's a separation technique. You're separating out any metal that you don't want to get through the feed. Again, it's a physical separation technique. When you separate it, you're not chemically changing anything. All right? Here we've got a picture to represent a visual representation of a mixture. It's got all kinds of different particles together in one container. That is a mixture. Okay? Now there are two types of mixtures. And I'm going to bring the whole thing up, and I'm going to just have you write them down. And then I'll talk a little bit about that term that you see there at the bottom, that term phase. Sorry, how do you pronounce it? Homogeneous and heterogeneous. So mixtures come in two types. Now, in our lessons here today, I'm going to be asking you various questions on different mixtures and various things. But to be honest, chemists aren't really that interested in mixtures. We're definitely not interested in heterogeneous mixtures. We tend to be interested in solutions, homogeneous mixtures, when we dissolve something in water. Perhaps it may react that way. But we're interested in the way the chemicals react with each other. So we've got a homogeneous or solution, uniform properties in composition, has only one visible phase, heterogeneous or mechanical mixture, non-uniform properties in composition, has two or more visible phases. An example of a heterogeneous mixture, rocks and sand. Oil and water. Yep. Yeah, that's what I was going to put on the board here. So I'm going to draw a couple of examples. I'm going to draw them on the board, but you can draw them just down below over here in between this definition of what a phase is. So on the left-hand side, I'm going to draw a little example of a homogeneous mixture. And on the right-hand side, I'm going to draw an example of a heterogeneous mixture. That's my representation of a graduated cylinder. Yeah, look like a graduated cylinder. And I'll put one over here to represent the other one. And the reason I draw it in a graduated cylinder is so that you can imagine what it would be like to pour that particular stuff in. So a homogeneous mixture, let's say we pour some water into that particular container, some H2O, and then let's say we put some salt into that particular container. And I don't know, do we know what the chemical formula for salt is? Does anybody know what that is? Chemical formula for salt? Some of you might. We'll go to a veteran event. They never put up their hands because they know, Jenny's going to put her hand up. All right, what do you got? It's not just Na. It does have sodium in it. What else does it have? Anybody know? Na, and what else? It's got one other type of atom in it. It's also got chlorine in it, NaCl. This is salt. Yeah, you should have. So you put some salt in water, and what does it do? Well, it dissolves. What does that mean? It means that all of the little salt particles separate themselves out. They spread out as evenly as can be, and you can't even see it anymore. There is no way to see the sodium and chloride anymore because it spread itself out completely. If I take some water and now I add some vegetable oil into it, it doesn't even have to be vegetable oil. It could be any oil. It could be motor oil. It could be gasoline. What happens when you add oil and water? Could be olive oil. Maybe you're making salad dressing. What happens to oil and water? Yep. Yeah, which sits at the top? The oil does. Very good. And even if you're making salad dressing, say you put a lid on it and you give it a good shake, eventually it's going to go back to the top, right? You've seen that before. Maybe you take some salad dressing out of the fridge and you go, oh my God, that's disgusting. You know, so you shake it up and then you put it on the salad and it's delicious. So anyway, so what is happening there? Well, the oil doesn't want to mix with the water for many reasons, which I'm not going to explain. But let's say that you mixed it up and you've got some bubbles in the water, but let's say that you can see that line where the water is sitting down there. If it's salad dressing, it's likely vinegar, and the oil is sitting there, all right? Now, this idea of what we call a phase, a distinguishable boundary, there is always going to be that line in between the water and the oil. And we would say here that this is the distinguishable boundary. This is the phase line, all right? So if you've got a mixture of oil and water, you actually have a water phase and an oil phase. So there are two phases in our mixture, and you can visually see the boundaries of those things. That's what makes it a heterogeneous mixture, all right? Now, I could have used something like throw some rocks in some water, and you go, and I'd say, can you see the rocks? And you say, well, yeah. Okay, well then that's a heterogeneous mixture, because there's a rock phase and there's a water phase, and it would be true. But I think salad dressing or oil and water kind of illustrates it a little better. So if you've got things that are mixed together and you can easily distinguish their boundaries, then you have a heterogeneous mixture. If you're looking at a substance and you can't see the difference between the two things, it's then a solution or a homogeneous mixture, all right? The air itself right in front of us is made up of a mixture of gases. Does anybody know what types of gases are in our atmosphere that's right in front of us? What type of gases do we have in our atmosphere? What's that? CO2. As we exhale or as the car drives by, CO2 is released into the atmosphere. Correct. What else is in the air? Oxygen. I would hope so. Our existence right here is proof that there's oxygen in the air. We inhale the oxygen. We exhale some carbon dioxide. Excellent. Does anybody know what else is in the air? Sorry? There is a lot of nitrogen in the air. The air is predominantly nitrogen. It's about 78% nitrogen, right, with about 20% of it being oxygen, and then the last 1% being tiny little bits. But in the end, it's a mixture of gases. There are oxygen molecules and nitrogen molecules and carbon dioxide molecules and some water vapor when some water evaporates. It's just like our solution, except it's in the gas state, but it's still a solution. In front of us is an example of a homogeneous mixture of gases that are mixed together. Now, I guess if you were to consider our classroom to be a container, and the fact that we're in the container, and I can easily distinguish your boundaries, in other words, I can visually locate where you are, you could maybe classify our classroom as being a heterogeneous mixture with a student phase, a silly thing to call it, but I can see your edges, and also the gas phase, which is the air. And that would be a true statement as well, okay, because I can distinguish your boundaries. Okay, so that's what makes mixtures. There we've got some images, and I'm not that concerned. Let's now move on to pure substances. So we've now gone to the left-hand side of our little diagram, and now we want to take a look at what's happening down the left-hand side. Question? These, I think I do want you to draw. If you haven't been drawing them up to this point, it's not a big deal, but these become more important. Ketchup would still be, you might think that you can just see a ketchup phase, right? But I think if we were to look closer at the substance ketchup, perhaps under a microscope, you would see some little individual particles that represent different parts. Is there oil in ketchup? I would think there'd be some, but it probably doesn't settle out. There's water, definitely. There would be then some solid particulate matter, perhaps from the tomatoes, that type of thing. I would think that that's probably a mechanical mixture, a heterogeneous mixture. That would be my guess. I would need to maybe do a little more microscopic investigation in order to identify it. But I think that would be the case. That's what we would discover. Why doesn't does ketchup separate? Because you get the water at the top, and you always get that, if you're the first one to use it, it sucks because all the water is separated out. Well, that would be evidence that it is a mechanical mixture, and that gravity is bringing the solid particles down, leaving the liquid component at the top. That would be my guess. Yep.
So the solid parts of like the ketchup or whatever, they count as the phase?
Yes. Yep. They would. Yep. Okay. Now to pure substances. Pure substances contain a single defining particle. They contain one particle that makes it what it is. Cannot be separated by physical methods. So you cannot break these pure substances apart by physical methods. You need a chemical reaction. There is no change in the particle composition during the change of state. When something is melting or freezing, and we learned that the last day, if it's a physical change, the particles stay together. So here are some examples of some pure substances. Here we've got iron. Now notice we've put it into a little example of a box, and each sphere is identical. That's because iron is made up of individual iron atoms together in a hunk of iron. But notice in this picture, I have oxygen. Oxygen is made up of two oxygen atoms stuck together. It's called O2. And so in this picture, we represent it with two oxygen atoms, two spheres that are the same, stuck together. Sodium chloride, salt, is also a pure substance, but it's made up of a sodium atom and a chloride atom put together. All right? Actually, right close to your pictures here, put here, and we haven't learned the symbols yet, but I'm going to put them down because you've heard of them before. Those are made up of individual Fe's, iron. And we'll talk about the periodic table tomorrow, but I think we've all heard of the periodic table before. This is made up of O2 molecules, two O's put together. I think we've seen that before in grade 10. And this is made up of an Na atom stuck together with a Cl atom. Again, chemically stuck together. Sorry? In a lattice structure. But for each of these substances, each of their molecules and atoms are the same. That's what makes them a pure substance. Each of the atoms and molecules are the same. Okay? You used all that page. That's good. Like right to the bottom. Nice. Like you're squeezing that last little bit in. How we doing? Jess, how we doing? Chris? Are you good to go? Are you writing on another device? Is that what you're doing? No. Oh, you're just waiting? No, that's fine. I'm just curious if you're ready to go or not, because I don't know whether people are using devices or not. Don't write this stuff down. Let's just do a little practice run. Let's classify this as being a pure substance or a mixture with a little brief explanation why. Let's take a look at this one. Would this be classified as a pure substance or a mixture? Conrad, what do you got? Pure substance. Pure substance. I like it. Pure substance. I'm just going to go PS. Why is that? There's only one kind of particle in there. Nice. How about this one? What is that going to be classified as? Yep. Mixture. Mixture. This one here? What is it going to be classified as? Anyone? What's that? Yeah, pure substance. Nice. Pure substance, because all of the particles are identical. Nice. And this one here, what is it going to be classified as? Yep. Pure substance. Even though it's got two different molecules that are kind of stuck together, or sorry, two different atoms that are kind of stuck together, they're all the same. They're pure substances. Okay? No way to tell by our illustration whether it's a heterogeneous or a homogeneous mixture, because this is an atomic view, all right? We don't know what the view is if we were to look at it out here, whether we could see more or one phase. But I don't care about that. All right, elements. To bring the whole thing up. So now we've looked at pure substances, and underneath pure substances, we can make a subdivision. So now we're going to look at all of these pure substances that we've just talked about, and we want to subdivide them into their own groups. So we just looked at pure substances. We're now subdividing them into their own groups. And so we're to the left-hand side of our diagram that we drew at the beginning, right? I just kind of drew that left-hand side. So up here we've got matter, right? And over there was the mixtures, and now we're over here on this side. This is the exciting side when it comes to chemistry. This stuff right here is what chemistry is all about, right? What we do as chemists is all about studying these pure substances and compounds. In actual fact, the desire to learn about elements is probably what drove early human beings to become chemists. So if we go way back to, I guess I say caveman days, right? Even before probably the development of speech, probably soon after the discovery of fire, human beings were burning things, right? That's what chemists do. Chemists study substances, and the way they study those substances is by exposing them to energy and seeing what they do, all right? I like to often think, and yes, you've heard this story before, but I like to often think about chemists as being kind of like an 11-year-old or 12-year-old male, right? Because what do 11 and 12-year-old males want to do? Well, they want to blow things up, and if they've got a fire going, what are they going to do? Burn what? What are they going to burn? Anything and everything. What is that? I don't know. Let's burn it. Hey, look, there's a frog. Let's burn it. Right? They want to burn everything. Now, that's what early chemists would have done, right? They would have found some red dirt. What should we do with it? I don't know. Let's burn it. I don't know. Who knows what? A rock, a shiny rock. What should we do? Let's burn it. Now, if you burn enough stuff, you're going to find that some of the stuff you stick in the fire does something. It reacts. It either, combines with something and turns into a new thing. We have a chemical change in color. Or maybe it breaks down into something that's more fundamental, right? You've probably heard of the Bronze Age and the Copper Age and the Iron Age. Those things would have been initiated by somebody burning something. Burning some copper ore that's mixed with some other chemicals, maybe with the ashes of a fire, does a reaction. In the end, this shiny metal came out, and they all went, ooh. And then someone decided to take that shiny metal and hit it with a rock, and they found they could bend it. And then somebody hit it with a rock enough to make a pointy surface, and then they... stabbed the guy beside him because they didn't like him very much. And then some war broke out, and the person with the most copper killed all the people that didn't have the copper. I don't know. I'm not a historian. But that's the way chemistry goes. It's all about investigating what these things do by adding energy. Fire. Fire would have been the first thing that chemists would have been looking at. So, take a look here. Element is a pure substance that can't be broken down into simpler substances by chemical methods. So maybe they found something, they put it in the fire, nothing happens. They make the fire hotter, nothing happens. What do they say? They say, wait, this must be something very fundamental. It must be an element, the simplest substance that can exist. We'll put it over there. It doesn't do anything when we heat the heck out of it. All right? This we call in chemistry an empirical definition. It means that we can see this with our senses. We burn it. Does it do something? No. It's an element. It's very simple. It doesn't break down. This is what we call a theoretical definition. It's an idea. If we believe that atoms exist, then maybe the reason it doesn't break down is because all the atoms are the same. And so the atoms aren't separating and they're not doing anything. So it must be made up of one type of atom. All right? The atom is the smallest part of an element that still has its elemental properties. I'm going to jump ahead here for a minute. I want to do the compound. Let's do the compound. Some of you already wrote ahead. Leave spaces. We are going to come back to those pictures. Yeah, but I've jumped ahead to compound. So I've jumped ahead a few slides. You probably could. Sure you can. If you haven't jumped ahead, write compounds, then we're going to go back. You know what? Have you started to write this already? Okay, just stop. Don't write. Let me just talk about what this is, then we'll go back and we'll write it. Let me just compare the compound with the element. That's the way I like to teach it. A pure substance that can be broken down by chemical methods. All right? They've got here water as the example, but you could use any compound. Again, like I said, they might have found some substance, threw it in the fire, and something happened. Some gas was produced, and something else was left behind. So whatever elements were in there separated out. Again, this would have been done with fire. With water, we can separate the hydrogen from the oxygen. We need some electricity. You may have seen that experiment in grade 9 maybe, called the Huffman apparatus. It had these tubes, and you plug it in, and it made a lot of noise, and some gases were formed. So we can use electricity to break a compound down. Again, this is the empirical definition. We can sense this in the laboratory. Contain two or more different elements which are joined by a chemical bond. This is the theoretical definition, because we believe there are two different types of elements in there. All right, so these are compounds. You can see they're made up of two different elements. Let me go back then to that. I just wanted to compare the compound with that. Let's go back to, whoops, I'm going forward and I want to go back, forward. Okay. So we're back talking about elements. We're talking about the things on the periodic table. All right? Our periodic table contains our knowledge of the elements. Some of these elements are made up of individual atoms. What is the next part that comes up? Arrow. Yeah, I'll put the examples in myself. I already put an example of an atomic element on a previous slide. Does anybody remember which element I put there? Iron, Fe. Any of these metals that we use as metals exist as individual atoms. So you could have gold, Au, gold. By the way, that's iron. And I'm going to just put here metals, etc. I've already given you an example of an element that's made up of a molecule where more than one atom is stuck together. Yeah, O2, oxygen. O2. Does anybody know the other gases that exist as two put together? By the way, we're going to learn this tomorrow. These guys in red are the gases, and some of them like to exist as pairs. And those people who are coming up with that answers probably had other chemistry classes. So if you're not knowing this, don't worry about it. We're going to be teaching you it. What do we got? Yeah. Does anybody remember maybe grade 9 or 10, especially if you had Mr. Williams? He would have talked about Hofbrinkel the clown. Remember that? I don't know if Hofbrinkel is just a goofy set of letters to represent all the gases that exist as two particles stuck together. So H is H2. Actually, I'll just write it down. It's silly, but it does help you remember. Hofbrinkel. So H is H2, hydrogen gas. The O of Hof is O2, oxygen gas. Anybody know what element is? Yep. Yep. Fluorine, right there. Fluorine is F2. Now, Brinkel, what a silly thing. Yep. Yeah, bromine. You'll notice it's a liquid because it's blue, but if you heat it a little bit, like it doesn't need to have a lot of heat, it soon turns into a gas. It becomes Br2. The I in Inkel. What a silly thing. What element do you think the I is? It's just I. What is the element? All right, Amy's up front. What do you see? Iodine. Yep. Or iodine. Doesn't matter how you pronounce it. It's I2. The N. N. Nitrogen in the air is N2. And coal. What a silly thing. Yeah, chlorine. Cl2. All of these elements are two atoms paired up. Now, you don't need to know this. I don't even have the university level kids worry about this. In university, you talk about this. It turns out that sulfur is actually S8. 8 of them stuck together in the shape of a crown. And there are many other elements that are made up of different numbers. They're quite complex. I don't expect you to know that stuff. We'll just worry about the ones that have 2. So those are elements that are 2 atoms stuck together as a molecule. A molecule is 2 or more atoms joined by a chemical bond. All right. Great. Examples. Awesome. That's nice. Compounds. You can now write down the compounds part. A pure substance that can be broken down into simpler substances by chemical methods. Fire is a chemical method. Electricity is a chemical, is how we undergo reactions. You can react chemicals together, and they can pull the atoms apart and release their elements. So you can use chemical reactions to do that. Light can sometimes do that. Light can pull them apart. HCl gas, hydrogen chloride gas, if it's hit with sunlight, will break apart. It'll break the bond. So any type of energy, you can even use mechanical energy. There's a chemical called nitrogen triiodide, and I should have maybe made it for today. That'd be fun. We'll save it for another day. Nitrogen triiodide is a contact explosive. You make it. If I hit it with like a feather, it explodes because it is so unstable. The compound breaks down into its elements just by the mere touch of a feather. Phenomenal stuff. If you want to do a YouTube search at some point, just YouTube nitrogen triiodide, and you'll get all kinds of them. So chemical methods can be as simple as a reaction. contain two or more different elements which are joined by a chemical bond. The smallest part of a compound that is still a compound is called a molecule. And so here they're talking about aluminum oxide, an aluminum atom and an oxygen atom, carbon disulfide, carbon atom with two sulfur atoms. We good to go? I don't know where everybody is. Did I get a no? Yes, no? Good to go, good to go? No? I think still fishing enough? Yes, good to go, good to go. See, Jessica is still working the pen and pencil. Are you? Are you sure? I'm not like scaring you. Don't have to write this stuff down. Just saying. Element or compound? Element or compound? Yep. Element. Made up of one type of atom. Element or compound? Jess, what do you think? Yeah, compound. Made up of two different types of elements bonded together. Element or compound? Conrad? Yeah, element. It is a molecular element. It could have been any of those Hofbrinkel ones that we've talked about, stuck together. Okay? All right, let's keep rolling. Pure substance or mixture, and if it's a pure substance, tell me if it's an element or a compound. Milk. What do you think? Milk. Any ideas? Pure substance or mixture? Milk. It's a tough one. We've picked a mean one. Did somebody say something? I'm only hearing mixture. Yeah, it is a mixture. What is in milk? What different things are in milk that makes it a mixture? Yeah, there's some calcium in it. What else? Lots of water in it. That I don't know. I could be. What about, what's the percentage that they always talk about in milk where they say 2%? 2% what? Fat. 2% milk fat, right? So there's milk fat. There's fat in milk. Like if you have raw milk that hasn't been like processed, and my mom used to always go to the neighbor's farm and just get the milk out of the thing, and we would have the milk. If you've ever seen that, what settles to the top? What floats to the top? The milk fat, and it's the cream part. And my mom would used to scrape it all off, and then she'd put it in another container to use for something else. But if you got to the milk to put on your cereal before she took the cream off of it, yeah, gee. It was like chewy. It's disgusting.
Does it taste gross?
Well, it doesn't really taste bad, but it's the texture. Thick cream on cereal just doesn't go.
So it's bitter and taste someone
Nope.
else.
Nope. No, it tastes the same. Yeah. They do, but that heats it up a little bit to kill any little whatever. But that doesn't affect the taste. Yeah, it's very similar. But it's like drinking homogenized milk as opposed to 2%. So the milk was like thicker than. So when if you drank a lot of it, too bad. But when I went to university and went from drinking this to buying 2% milk, I was like, it's water. What the heck's going on here? There's nothing to this milk. You know what I mean? So yeah, there's a thickness to that. All right, excellent. Gold, pure substance or mixture? No, don't worry about it. I got a couple of sheets on Google Classroom that you're gonna do yourself. Gold, pure substance or mixture? Yep, pure substance. Is it an element or a compound? Someone else. Amy, your arm's got to be getting tired. Conrad? How do you know? It's only one, and it's found on our table of elements. Element. It's only one. That's correct. Magnesium chloride, pure substance or mixture? Yep. No, it's not a mixture. No. Yep. Well, that's 50-50, so good job. Nice. Pure substance. And, yep, it's a compound. It's two of those elements put together as one. Even in the name, two elements put together as one. If it was a mixture of magnesium and chlorine, that'd be different. We'd say magnesium and chlorine, two elements kind of dumped together in one bag, you know, or something like that. But this is magnesium chloride, which means they're bonded together. The "ide" tells you that, all right? So this is a compound. Compound, nice. Okay, moving on. The two more pages of just questions. Again, we're not writing them down because I'm just going to get you to work. Indicate whether each of the following represents a pure substance or a mixture. If it's if the substance is a pure substance, tell me if it's an element or a compound, and if the element is made up of atoms or molecules. If the substance is a mixture, is it a mixture of elements, a mixture of compounds, or a mixture of elements and compounds? Woo! What a bunch of questions. What is this? What is this representing? What's it representing? I'm going to pick on some other names here. What we got? I know Brienne's name. Brienne, what is this? What do you think? All these dots that are the same. Sorry? Pure substance. Oh, my pen isn't writing. Pure substance. I agree. Is this pure substance made up of an element or a compound? Is this an element or a compound? Yeah, it's an element. Because they're all the same, right? And they don't have, they don't have two different dots. This deals with mixtures, so I'm not worried about it. Let's go over here. What is this? Yep, it's a mixture. Mixture. So does this mixture have a mixture of elements, or a mixture of compounds, or a mixture of elements and compounds? What's in this? Is it different elements? Or is it different compounds? Or is there elements and compounds in this thing? Conrad? Both elements and compounds. Elements and compounds. Elements and compounds. Because they're made up of, oh, wait a minute. Ooh, I want to look closer at that again. What has to be true about the circles to make them compounds? They have to be different colors, don't they? Right? These are all the same. These are the same. Wait a minute. We don't have any that have the two different circles, right? So that makes them all elements, because this could be O2, this could be H2, this could be a bunch of different metals. Those are all elements. You almost had me sold. I did the same. I looked at these two, like you thought, Conrad. But see how they're the same? That makes them all elements. Let's look at the next two. The question's the same on this one. What is this? Mixture or pure substance? Mixture or pure substance? What do you think, Jess? Mixture, I agree. Mix. So, does it have all elements? Or is it all compounds? Or are there some elements and some compounds? Both? Element, element, compound, compound, compound. Both. Both. Make sense? What's this? Yep. It's a mixture. And what are in these? All compounds. Different dots. Everybody starting to catch this? This is all compounds. And what is this? Yep. Pure substance. And it's all, ooh, are the dots different? They're all elements. This could be like all O2, right? Or all H2. Those are elements. Okay, so on Google Classroom, I have 2 sheets for you to do. That's what you're going to work on right now. So if one of them does. The one that says assignment is the one that I'm going to mark. When you turn them in, you will turn in both. I know the way you guys think. You'll just do the assignment one and just turn it in, and you won't do the practice one for practice, because that's just how you are. I could, what's that? I could maybe just look at the other one for completion and give you a tiny mark for completion. You see what I mean? So I'm going to look for completion, that it's done, and then I'm going to look closely at the other one. All right, and I'm going to bring up Google Classroom here for a moment just to show you, but I think you guys know where it is. So you guys can go ahead. You don't have to wait for me. What? Web page unavailable? Are we down? I wonder if I lost my internet connection when we went down. I need a new sign-in. There we go. Oh, I'm recording a spinning wheel. I think I'm going to stop recording.